So, hello everyone. So, welcome to our this week Rutgers Efficient seminar. And today we are very glad we have the Professor Alexander Rush from the Cornell University. And right now he is an associate professor at Cornell Tech NYC. His group's research is in the intersection of the natural language processing, deep learning, and the structured prediction with application in text generation and the efficient inference. He contributes to several open source projects in NLP and works part-time at Hugging Face. He's on the board of ICAR and developed the mini conf tool used to run ML NLP virtual conferences. His work has received a paper and demo awards at major NLP visualization and hardware conference. And he received the NSF Career Award and the Sloan Fellowship. So now let's welcome Professor Rush to give us this talk, Pushing NLP to the Edge.
Thanks everyone for having me. Hopefully my sound's going through well. I'm still kind of getting used to Zoom talks. So today I'm going to talk about work that my group has been doing on this topic of pushing NLP to the edge. This is a combination of a series of 3 or 4 papers that were written at Cornell and some at Hugging Face. Cornell, I hope you know, is a university. Hugging Face is a small startup in New York City that works on NLP technology. This was work with my collaborators, Terry Tambe, Victor San, Demi Guo, Yoon Kim, Francois Lagunas, Ella Charlet, Thomas Wolf, David Brooks, and Gu Yan Wei. So because this audience is kind of a general purpose audience, I thought I would start with a short introduction to natural language processing. Natural language processing is a topic, well, I've spent my whole life working on. It's a topic I really love the nuances of and the specific properties of how language works and its structure. But I understand a lot of folks are more interested in the applications of NLP than some of these nuances. And in fact, if you're interested in NLP applications, it's kind of a perfect time to get into the field, particularly because there's been a kind of convergence of technology that makes it possible for many different problems in NLP to be solved with very similar methods. So let's do a kind of much too short introduction to NLP as an area. In particular, in these couple slides, let's just go through some kind of basic models that we'll be using throughout the talk. So in general, I'm going to write things in this schematic form, where we have a blue model that takes in some text and makes some prediction. I represent the blue model as a black box because the particularities of its structure will really not be that important to the talk itself. In general, we use architecture known as a transformer for a lot of these prediction tasks. But for really most of what I'm saying, you can think of it as very similar to a kind of feed-forward neural network. Now, when working with language, we feed in language at the bottom of this model and get out some prediction at the top. And perhaps the simplest problem we work with in the field is known as text classification. So in text classification, we're going to take in a sentence, in this case, movie review, and put out the number of stars that we think that corresponds to. So do we think it's a positive review? Do we think it's a negative review? Do we think it's in between? And in general, this data set goes under the name SST2. And throughout the talk, I'm going to refer to it as being part of the series of benchmarks known as GLUE. And GLUE is basically a collection of tasks with a roughly similar form to this that we use for benchmarking kind of basic natural language processing models. Now, I do want to emphasize a little bit some of the complexities in this task itself. So given a sentence of this form, there's really more going on here than just kind of finding kind of positive or negative words. So you might notice in this example, there's this word chiaroscuro, which corresponds to an Italian cognate representing a kind of darkness underlying the shade of the imagery. And this is a word that almost certainly the model doesn't see in its training data. So it has to kind of understand what's going on in this word, how it connects to the other words in the sentence, and utilize that to determine whether it corresponds to a very positive word, a very negative word, or one in between. Another task we'll talk about throughout this talk is the SQUAD benchmark. In SQUAD, we have a slightly more complex task of question answering. This is a particularly important task for a lot of industrial use cases where you may have, say, a knowledge base of, say, a company documentation, and you want to be able to ask questions about it to find answers. In SQUAD, you're going to take in two sequences of text, one that corresponds to a paragraph from Wikipedia, and another that corresponds to a question. The output of this model will be some series of words where, in the case of SQUAD, those words correspond to a contiguous sequence in the Wikipedia article. So in this case, when asked who headlined the halftime show of Super Bowl 50, we're going to get out the word Coldplay from the article itself. And really, I just mentioned SQUAD because it's become a kind of standard benchmark for these sort of efficiency tasks. We're going to basically be measuring our accuracy on it by how good we are at identifying the start and end positions in the original sentence. And just to emphasize some of the difficulties here, to understand and answer these questions, we have to have a model that understands all the relationships in the Wikipedia article, that distinguishes the band Coldplay from two other entities that also look like musicians, and determine that that is the key thing to return for the article itself. So again, we're kind of going beyond simply just looking at words we know to looking at the relationships with the words and the words in context themselves. So just to summarize that, we're going to kind of define NLP in a very naive and obviously completely oversimplified way as kind of being about these three different areas. We want to be able to understand and know about kind of complex words we're interested in. We want to be able to distinguish complex relationships. And in particular, you'll note that we're kind of adapting a general purpose model to many different tasks. And kind of nailing these three areas has been really important for getting kind of the state-of-the-art performance in many natural language processing tasks over the last 5 years. Now, the main way we do this, and I think it's going to be a little less satisfying than you might want, is to utilize a pre-training approach in order to basically learn as much as we can about general purpose documents written in English or in whatever language we're interested in. And we do this by a general recipe, which is known as pre-training. And the way pre-training works is we define a third task. And this task is similar in some ways to the previous two. We're going to take in a sequence of words, and we're going to make predictions about those words. And in particular, we're going to take in some arbitrary text from the internet. We're going to mask out or blank out some percentage of the words. And then we're going to define our task as predicting those words back. So here our output will be exactly the same as what we took in, but wherever we had a blank space, we're going to have a multi-class classification problem where we're going to need to predict one of the words in the English dictionary that we think best fit in that blank space. And what's so important about this task is that we can get almost infinite data for it. We can build models that are as large as we can fit on our hardware. And we can then use this as a way of attacking the earlier challenges in NLP. If we see enough text, we're going to learn about every word that we could possibly see in English. If we see enough text itself, we can figure out what the relationships are by kind of solving this fill in the blank problem with other words in the area around it. Once you have one of these pre-trained models, then you can utilize it for the last or the third challenge of applying it for many different classification tasks in natural language processing. So to kind of describe this relationship, we're going to have 3 steps that we're going to work with. We're going to have a pre-trained step where we learn as much as we possibly can about general purpose language in an unsupervised manner. We're then going to have a bunch of tasks like question answering or text classification. Each of these will start with this pre-trained model, be fine-tuned for their individual domain, and then be deployed on the right-hand side for our application of interest. And in some sense, this is really kind of all you might need to know about NLP as a practitioner. If you get this right, kind of rough trade-off, you can kind of slot in any of the fine-tuned tasks you might be interested in. Cool. So I'll give a brief plug. So this startup Hugging Face I work with is kind of collecting and cataloging all of these different NLP models and data sets. If you're using NLP for your own tasks, you can kind of get many different versions of these pre-trained models online for free. And then you can adapt it to many different data set tasks. So there really is a kind of N by M relationship here. There are now hundreds of different pre-trained models people have built, and there are thousands of different data sets people have tuned them for. And in many ways, NLP, unlike a lot of other areas, is really about kind of many different data sets for many different problems of interest. Great, but this talks about efficiency, so let's get on to efficiency. So let me set the stage a little bit for why efficiency is so important in natural language processing. So as you can imagine, the bigger these models are and the more data they've seen, the more words and the more relationships they've seen, and the better they perform on new tasks. So if you can make the different stages of this pipeline fatter, then you can get better accuracy in the middle areas of the task itself. But if you do that, you also have the problem that the application you're actually deploying on the right gets larger as well. The benefits from making pre-training larger become kind of deficits when actually deploying and utilizing the app on the right. So we found that kind of the best way to increase performance is with bigger models, but now we have a whole challenge of kind of actually figuring out how to use these models in practice. And practically what's happened is we've kind of gotten bigger and bigger models over the last couple of years. So this graph only goes to 2020, and it's already kind of making the point quite strongly, where models are going up to kind of, I don't know, hundreds of billions of parameters, while still seeing gains. Whereas in practice, I think most practical users are still kind of around kind of 2019, in that they haven't really been able to take advantage of the much larger models, because even these models coming out in 2019 are too large for a lot of different applications to be used. So that's going to be the focus of the talk today. I'm going to go through some vignettes where I talk about different kind of algorithmic methods for making it possible to deploy these large models. So I'm going to basically assume the first step is completely fixed, that we have access to kind of a large pre-trained model that we're interested in working with. I'm going to call that model BERT, just because that's the brand name that kind of was most commonly used when these papers are written, but there are many others that you might slot in for that slot. And we're going to be interested in how you might fine-tune BERT on many different tasks, and then how you might deploy those to an edge device. So how you might actually utilize BERT for many different tasks within an application that you're actually deploying. Cool. So let's start there. So the outline of the talk is I'm going to talk through 3 different algorithmic ideas, each of which of these is kind of around the theme of how do we co-design to facilitate NLP models to deploy on end user devices. And just to give a little bit of a caveat, my background is strictly in the ML side, and so I'm thinking about this as kind of targeting a specific use case that I've been told is useful. And a lot of this is motivated by conversations I've had with people who actually know the hardware itself and actually can provide some insight into what the challenges are and the challenges for actually using it. And so I'll end the talk by discussing a little bit of a kind of full system that takes into account these and other ideas to actually deploy models to devices. Great, and then I should also mention, if you have any questions, feel free to stop me. I can also see the chat and can answer questions as I go. Cool. So the first part of the talk is going to focus in on this idea of pruning, and particularly the relationship between pruning and fine-tuning, this middle step where we actually kind of adapt the model to the particular task of interest. And so our first goal is going to be to just eliminate parameters that we don't think are important for a specific fine-tuned task. So starting with BERT, we're going to be interested in doing question answering. We're going to fine-tune the model for question answering, and we're going to eliminate parameters that we don't think are useful. So first off, let me motivate why this is important. So one of the kind of benefits of this is to produce just smaller models to send to the device. So one kind of obvious way this is beneficial is that smaller models require kind of less bandwidth to send them over to the edge. But another reason that I think was less intuitive to me is just that smaller models are going to require less energy. So if the majority of the energy consumption is actually fetching and loading these weights, if we can just make the weights kind of much smaller and easier to use, then we can get a benefit here in practice. Okay, so the first thing I'm going to do in each of these vignettes is talk a little bit about what the obvious baseline might be. And in particular, for this style of pruning, there's a really nice baseline that seemingly is both very simple and works extremely well. So the baseline is the following. If we want to make our neural network smaller, we can simply apply magnitude pruning. That is, we take the absolute value of each of our parameters. If they're below a certain threshold epsilon, we can just get rid of them. And we get this small sparse model on the right that has many fewer of these parameters. This approach can also be extended with some additional tuning, where we keep the mask of the parameters fixed to 0 while tuning the blue weights in the diagram itself. And doing that's a quite strong baseline for this problem and can be used relatively well for lots of problems and has been used in a lot of different areas of deep learning. So let me talk a little bit about the challenge of this approach. So remember that the particular case we're interested in is the case of pre-training, then fine-tuning, where we don't know at the time of pre-training what the fine-tuning task is going to be. So we note the following property of magnitude pruning. If we start with a pre-trained model, all of our different parameters are going to have a specific weight. We can graph those where the x-axis of this graph shows the weight of each of our pre-trained parameters. When we do fine-tuning, the way it works in NLP is we move all the parameters. But in order to avoid kind of immediate overfitting to the small fine-tuning domain, we run with actually a relatively small learning rate. And what that means in practice is that very few of the parameters actually move that far from their pre-trained value. I think I have a color next. So if I look at this red color, it basically shows that in practice, the parameters that get pruned by magnitude pruning are the parameters that were small in the pre-trained model. So there's no adaptation to the fine-tuned task. We just basically pre-train a bunch of parameters, prune them, and then get many fewer actually active parameters in our fine-tuned task itself. So the main idea we're going to propose is to have a kind of adaptive pruning that targets the particular fine-tuning tasks themselves. So to do this, we're going to utilize ideas from this kind of adaptive pruning with a method we call movement pruning. And the way it's going to work is we're going to have a mask that's learned specifically for each task of interest. And that mask itself will allow us to prune out the parameters that we think will matter for that task. So we take a loss here where the loss goes back to the task itself, but also updates our underlying mask structure. So this is based on some work in computer vision. I'll go through some of the methodology here step by step. So we're going to have 3 different matrices. So this is for basically every dense connection in our network. We're going to have a score matrix. We're going to have a mask matrix, and we're going to have a weight matrix. The mask matrix is computed by running thresholding on our score matrix. It will be 0s and 1. And we experiment with several different types of thresholding in the paper. And I think the final one uses a kind of top K masking to construct the matrix M. We then actually compute the activations in our network by applying a mask on top of our weight matrix and then applying it to the input X. In practice, this produces some set of activations based on this sparse weight matrix. At test time, we can throw away the score matrix altogether, throw away all parts of the weight matrix that we're not using, and send down in a kind of compressed sparse representation only the parameters of the weight matrix that are used. Now, to train the model, we experimented with several different approaches. And we settled on a straight-through training method for this paper. So the issue here is that the weight matrix is going to be a non-differentiable, or it'll have basically 0 gradients. And so in order to actually update the score matrix, we need to take into account that structure. So the way this works in practice is we're going to apply the thresholding, apply the mask during training, and then apply the straight-through gradient estimator based on the gradients the weight matrix gets back in practice. If you go through the math here, we'll see that our score matrix basically will reflect the parameter values that were having a large impact for the particular task in training, task in fine-tuning. So we actually get updates on our score matrix based on the fine-tuning task itself, as opposed to kind of the 0th order parameters that came from the pre-training method. And we can identify this in practice. So if we go back to this diagram, remember before that the pruning was based primarily on the x-axis values, which were based on how the parameter was used during pre-training. Whereas in this approach, we get kind of the parameters that were kept in yellow reflective of how much they moved during the fine-tuning step for our data. So I'll go through some experiments that we worked on. These experiments were on the data sets that I discussed earlier. So we apply several different variants of pruning and distillation-based methods. And these experiments are on the squad data set and several of the glue data sets that I mentioned earlier. So the main result is that we get about 95% of BERT's performance with about 5% of the encoder parameters. So here we see 2 different experiments, one that allows 10% of the parameters and one that allows 3%. The orange line here reflects the original value of the BERT model, which is at the top of this graph. And here we're comparing magnitude pruning versus movement pruning. So this is kind of strong magnitude pruning baseline that's able to tune the remaining weights of the parameters. And movement pruning at these levels of sparsity is performing much better. And again, we attribute much of this to the fact that it's utilizing the actual data itself for the actual task it's fine-tuning on as part of the pruning procedure. What we find in particular is that these models are very strong at very low or very high sparsity values, very low density values. So these graphs compare a bunch of different approaches that give sparsity on these domains on 2 of the glue benchmark data sets. So the BERT line is at the top in kind of the thick line here. And the dotted line represents 95% of accuracy. There are a bunch of different baselines here, including a smaller version of BERT, which seems to decline quite strongly pretty early on in terms of size. And then some other approaches, like I mentioned before, magnitude pruning, which starts out quite good, but when it gets toward low sparsity, really declines in terms of its accuracy. So the movement pruning baselines here, MVP and SMVP, will be quite strong even towards the lower part of the system. We also compared to several other approaches, which I'll mention later in the talk. Some of these use methods like distillation in order to produce smaller models, and some of them utilize forms of dropout, such as layer drop here, which tries to remove full layers of the model. And this model kind of starts going down pretty early on in terms of sparsity, although I'll talk about some of the benefits of distillation in the next section. Great. Okay, so that's kind of the base approach I'm going to use throughout the rest of the talk. So if you have any questions about how movement pruning works, feel free to ask now. Otherwise, I'm going to talk about 2 extensions that improve this approach for different use cases. So the first I'll talk about is a method known as block pruning. So in the first part of the talk, we were interested in just reducing the number of parameters that we send to the edge device. But if you've worked with pruning before, you're probably aware that simply just reducing the number of parameters is not really enough. What we'd really like to do is reduce the number of parameters and actually make the app much faster to run on the device itself. And in practice, this is actually quite difficult to do because if we send down kind of a compressed sparse matrix, it doesn't actually tell us how to actually compute this value in practice. The way we did this in training was we just treated it as a dense matrix with a lot of zeros. And if we do that on the device itself, we're not going to actually get a speed up. Kind of lacking specialized hardware or specialized structure, it's difficult to make these sort of matrix multiplies efficient on device. So there's a kind of series of other approaches that do make models more efficient to run. And in particular, there's an approach known as knowledge distillation. Knowledge distillation is actually one of my favorite approaches for efficient NLP. It's just extremely cool and elegant. You can use it in lots of different applications. So the way knowledge distillation works is that we start with a teacher model. And that teacher model will have a structure, a kind of probability over our output class Y, conditioned on our input text X. And it will have some parameters theta that we've learned. In this case, the parameters theta would be from fine-tuning BERT on a particular task. We then have a student model with parameters sigma. The student model has the same probabilistic structure, just a different set of parameters. And knowledge distillation doesn't touch the internals of the model at all. It just tries to make these 2 distributions similar. So what I show below is the simplex of these predictions. The prediction on the left is the specific thing that the teacher predicted, so a probability between 3 different classes. And what I'm showing on the right is the loss function that gets back propagated to the student model. And the goal is to use distillation to train the student predictions to mimic the distribution that the teacher outputted. Now, the benefit of distillation is that we get to decide what sigma looks like. So we can pick a smaller model with whatever sort of dense structure we might want to actually run on the edge device. We can make the model simply smaller matrices, or we can have it be a different architecture, or we can even kind of do things that are specific to the kind of, say, phone or edge hardware we might be interested in. It also gives us a way to utilize much larger models during training, and then knowingly produce a smaller model that we'll use in practice. However, as we saw from the last talk, pruning has some really nice advantages. Distillation gets around, I would say, 40% of the size of the original model, but we just saw we could get down to almost about 5% and really reduce the number of parameters. We also don't have to kind of produce a different model or search over kind of sizes or structures of the model we're interested in. We just take the original model structure and prune things out as we go. This also makes it much easier to target specific tasks as opposed to kind of producing a bunch of new distilled models to work with. Now, thankfully, in practice, these two approaches seem to stack well together. So you don't really need to pick one or the other. And in this talk, we'll present some results where we run distillation on top of a movement pruning-based approach. But in order to make the movement pruning approach kind of efficient at all, we have to get rid of these kind of sparse, unstructured matrices. So if we look at the actual output of a mask M, we get something like this, really like parameters all over the place in a fully unstructured way. In this work, we're really going to focus on trying to get a block sparse structure. So we're going to try to produce matrices where we have clear blocks of parameters that are on together and not just allow them to be all over the place in the matrix. And this sort of block sparse structure is one of several different types of structured matrices that people kind of know how to run efficiently on different types of hardware. And in particular, there are nice ways to run this on GPUs efficiently. And as part of this work, we put out a library to run them in practice. Now, the kind of algorithmic tricks behind the scenes here are all about kind of grouping together the sparse parameters in this block sparse way. In practice, it's not going to look so different than what we did in the previous talk, so I kind of won't go through all the specificities of the details there. But just note that in this work, we're kind of forcing it to either be on or off in a full block by itself together. So in particular, if we kind of look at the diagram from the last slide, we're going to still be running a score matrix where we have a score for each of the individual parameters, but we'll choose whether or not to actually keep a block of parameters on together. So the decision of whether to keep each of these three blocks will be done with a block sparse thresholding that takes into account all of the different individual parameters in that group and whether or not that is kind of above or below the threshold for keeping them around. From that, we can then block out whole parts of the matrix itself and back propagate again with straight through to the individual parameter scores. This will require us, again, keeping around a score matrix, a mass matrix, and a weight matrix, but a score matrix that we can dispose of at test time, and a mass matrix that we can just apply on top of the weights that we have available. Now, this is the only slide I'll talk about that gets into some of the specificities of transformer. One thing that's nice about blocks is that, as I said earlier, you can run them kind of efficiently on GPU. But one thing we found in practice was that when we apply these, they have a nice structured form. So most of the time we found that in these diagrams, the blocks were kind of taking out entire columns of our matrix simultaneously. And when this happens, you actually get particularly nice properties of the transformer itself. We can remove entire neurons, kind of propagate forward, and remove things of future matrices that utilize those neurons. We can also remove entire attention heads and sometimes entirely removing aspects of a transformer that had to look back in time in the model itself. So what this means is that a lot of the feed-forward networks become much simpler, and a lot of the attentions get either removed entirely or are more efficient to run. So this gives us nice speedups if we use these kind of block sparse kernels. But in practice, since that requires extra work, you can actually get most of the same benefits without using them at all. So this was a nice property that we didn't expect at first, but kind of came out of training in practice. Okay, so let me talk a little bit about some of the results. So in this work, we're considering both speed and pruning efficiency versus a range of benchmarks. So in the last paper, we're really focusing on reducing the number of parameters. Here, we're going to focus on a trade-off of efficiency and pruning efficiency. I'm going to show 4 different versions of this method. So one with only block structures, one that prunes out blocks and columns, and then one that prunes out blocks and columns and particularly has an extra projection step to remove columns that are close to being removed. And then finally, we have a version hybrid filled LT, which utilizes a distillation step in addition to pruning. So here we kind of prune to determine the structure and then distill to actually make the model more accurate in practice. And we're comparing to 3 different baselines. So 2 of these are distillation-based approaches that produce smaller, dense models. And then one of them is an approach called mobile BERT that uses a lot of kind of custom techniques to target efficiency on edge devices. So here are the 2 main graphs. So on the left, we have speed up of the model. And on the right, we have density. Both of these have as their y-axis the accuracy of the approach. And these graphs show the SQUAD benchmark. In the paper, we have a bunch of different benchmarks, including SQUAD, the blue benchmarks, and some benchmarks for a summarization task. So let's first look at the speed up graph. So the dot on the far left is BERT itself, which we have it speed up as 1, and it gets to an accuracy of about 88.5. Some of these models you'll notice will be above that, and that's because they use distillation from a larger BERT. So they actually can be faster and more accurate than this baseline BERT model that we're using here. The blue line shows a version of movement pruning. So that was the method I described in the last talk. And that method has a little bit of a speed up, but not much in practice. And it loses a lot of accuracy to get that speed up level. The other approaches show versions of block pruning that use kind of more and more advanced techniques to remove rows and blocks from the matrix. So in particular, if we look at the red line, that's the hybrid filled approach. It's nearing BERT performance while getting large speedups on this task itself. And it actually has higher accuracy than distillation-based approaches and also higher levels of speedup. Mobile BERT, which is at the top, uses, as I mentioned earlier, kind of larger BERT models to distill from, so it can actually achieve higher performance than our kind of baseline BERT model. But we're also able to achieve those levels of speed up if we employ similar distillation techniques. And that's that purple line at the top, which is one of our best models. But the kind of main goal of this was that we can get these speed ups while also reducing density. So distillation's a pretty strong baseline, but as you can see on the right, distillation only has about a kind of 50% sparsity of the models, or 50% size reduction, I should say. And all of the different movement pruning baselines have a kind of much higher sparsity, much fewer parameters to have around. And some of them are comparable to movement pruning, which we saw earlier, the blue line, while also having the speed ups on the left. We get the best of both worlds of kind of reducing model size while also getting speed up in practice. And to give you a sense of where this speed up comes from, we look at employing different block sizes in the model itself. So you can think of movement pruning as having block size 1, which is the blue line. And as we go from block size 4 to 8 to 16 to 32, we're seeing larger speedups of this approach because it can take advantage of the structure of the matrix and nearing kind of as we go out the performance of these other distillation-based approaches. Great. So the last thing I'd like to talk about is one other extension to movement pruning that targets some of the particular use cases of these pre-trained models in practice. And this approach is known as diff pruning. Diff is kind of taking inspiration from a kind of diff in programming, where you might only change a small part of your code to change a particular feature. So let me describe the goal here. So our goal in this project is to optimize parameters across tasks. So we're going to assume that we have a single application, but it might need to run many different NLP tasks on device. So in the previous two ideas, we were assuming we knew a single task that we had to send to the edge device. Whereas here, we're going to assume we have, say, 30 or 50 different tasks that all need to be sent to the device itself. And this is particularly notable in practice because the baseline approach here is pretty naive. I mean, if you're going to just take BERT and fine-tune it for 30 different tasks, you end up with 30 times the number of models on the device itself. Cool. So there is a kind of somewhat better baseline for this task, which is known as adapters. And the idea behind adapters is we're going to actually open up the black box and get in, and we're going to modify the black box for the given task of interest. So the way adapters works is that we add this extra layer called an adapter layer into the neural network and only learn the parameters of that new layer. So all the other white boxes here correspond to things that came from BERT in a pre-trained sense. And all the yellow ones represent things we're learning for the task itself. And if you do this, you can learn lots of different adapters that get applied for different tasks. And at test time, you keep around the BERT parameters and you swap in different adapters. This does require kind of getting into the model itself, though, and actually changing the architecture to run on device. So the approach we're going to explore in this paper is, instead of doing this, we're going to utilize the original structure of the model. It's kind of a theme of this talk a lot, is that we don't want to kind of change the model structure. We want to keep it the same, just kind of mess around with which parameters we actually change. And we're going to try to find a set of parameter diffs for each task that only change a very, very small set of parameters for that task itself. So instead of trying to prune the parameters down, we're now kind of building the parameters up. We get, say, 1% of parameters that we're allowed to modify in order to do question answering or text classification or whatever task of interest we are doing. So just to come back to our matrices, in this case, we're going to keep track of these scores that tell us how much we want to utilize a parameter. And then we're going to have a mass matrix M, and we're going to apply it to X itself. And sorry, this should have an extra paren on the outside. But the idea here now is that the mass matrix is applied to the diff scores in order to determine which ones of those we get to actually utilize. And then that's added to the weight matrix. So we're allowed to utilize the whole weight matrix now. We get all of BERT's parameters, but they're all fixed. The thing we're limiting in our budget now is how many of these extra parameters we get to include. So I have one more diagram. This might make it a little more clear. So if we have our pre-trained model parameters theta, these represent the parameters of BERT. We're only allowed to learn this diff vector delta. This is going to give us a task-specific parameterization, theta sub tau, where a very small set of the parameters get to change, and they're changed based on the task-specific loss. So our objective is going to be to fine-tune this model, where we have a regularization penalty that tells us we're only allowed to include so many extra deltas to change the weights for that task itself. Okay, I do not have enough time for the specific details, but in the paper, we actually utilize a kind of a different approach for this problem. We use what's called a differentiable approximation to the L0 norm. This is based on a previous approach, and we found this gives kind of very sparse and relatively accurate diffs for the given task of interest. In the paper, we also explore a group sparsity property, which is similar to the last vignette, that allows us to turn on groups of parameters that are near each other simultaneously. Okay, so just to kind of summarize, we're going to start with BERT. We're going to then fine-tune on dozens of different tasks. Each of the tasks will result in a diff, which we then send to the device. To actually run a given task, the device sums on the fly the diff onto its fixed BERT parameterization, and then makes predictions on the given tasks. To swap between different tasks, you just swap between these diffs, and you try to produce a different result. So the notable thing about this work is that we're really kind of pushing the limits of sparsity here. So we're going to be much more sparse than the previous pruning-based approaches. So using adapters, the approaches with kind of high accuracy require around 3.5 or 4%.
还没完，还没结束。
Sorry, was there a question? Cool. Require 3.5 to 4% of the parameters remaining. And you can get to about 80.4% accuracy on glue with that approach. The diff pruning approaches, we have 3 different versions of them, get to about 0.5% of the total BERT parameters while maintaining a roughly similar score. So we get to 79.4 on glue, or with kind of structured block pruning to 80.6. So it's roughly the same accuracy as the original model, with only changing 0.5% of the total parameters. So that's pretty neat. And the reason that number is so low is because you still have access to all the non-fine-tuned BERT parameters. We're really only counting kind of the number of additional parameters we've changed. But what that means is if you have kind of 12 tasks, you basically can run them without any new parameters, or kind of roughly 0 extra parameters, versus before you'd have to have 12 times the number of parameters for the task itself. One other thing to note is that I think I'm always surprised how poorly things like last layer tuning do. I know that's a very common benchmark in computer vision tasks and seems to work really well. But there seems to be just something different about how transformers work or how NLP works, such that just tuning last layer is actually not a very strong baseline. Cool. One thing that is interesting about this is that you can look at where the parameters actually get added. And we find that they get added in very different places across different tasks. This is not to make any kind of claim about the kind of semantic meaning of different layers of these models, just that there seems to be kind of no consistency about what's actually getting changed in practice. So my main point here is that there doesn't seem to be a kind of specific subset of BERT that's useful. It seems to be a different subset that might get turned on for different tasks, or maybe redundant subsets that get kind of turned on kind of randomly for given applications in practice. Cool. I think this is just kind of putting things back together again, these are several of the benchmarks that I mentioned from previous talks. And so things like Distilbert, if we're actually talking about the sparsity in terms of kind of the number of extra bits that need to be sent over the wire, they're not that sparse. So 40 to 60% of the original parameters remain, whereas with approaches like diff pruning or some of the more advanced block pruning, you're really talking about different orders of magnitude in terms of size. So you really can get much smaller while maintaining similar performance. And if you can figure out how to run them efficiently on device, then you get kind of the best of all worlds. Great. Okay, so I want to end by talking a little bit about kind of systems use cases of these, and I realize I'm almost out of time, so I'll go through it pretty quickly. But I definitely wanted to talk about this slide and note that tons of work has been done over the last year. The baselines that presented in these papers were kind of the baselines at that time, but a ton of other people have kind of improved upon them. So there's a lot of really interesting methods that are definitely worth checking out if you're interested in this area. So what I really like is this approach called BitFit. So BitFit looks kind of like diff pruning, except instead of deciding where the diffs are, it only tunes the biases of the model. So just only diffs the biases. And with that, you can get very, very few parameters and still maintain really accurate performance. There's also a bunch of different adapter-based approaches that have done relatively well, maintaining high score and training relatively few parameters. This graph's a little bit unfair to prompt tuning, but prompt tuning has been a really popular method for doing a kind of multitask training by basically learning a specific prompt for a given task. And lots of really interesting work in that space going on, both for kind of small task adaptation, but also for kind of really interesting new applications in NLP. And the last thing I'll mention is that as a kind of part of this project, we've been working with system architects to actually deploy some of these approaches and to build accelerators. And so in this work, Edgebert, a student, Thierry Tambay, I mentioned on the top of the slide, build a kind of full-on BERT pipeline applying many of these different approaches in practice and really measured the kind of energy use and application of these in edge devices. So in this approach, we're really combining all the tricks. So quantization, pruning, removing attention, doing an approach called early exiting to try to produce a kind of smaller, faster model. Cool, and I'll end with some pictures of this and some notes that these things in practice really do reduce energy a lot when utilized on the edge. Great, so thank you very much, and I'll stop here for questions.
Thanks for the very informative talk. And so, any questions from the audience? You are free to unmute yourself to ask a question. So maybe I can start question first. So I was wondering, so have you ever considered the kind of joint effort of also including the quantization here? So what will kind of the sensitivity for your compression approach if you can combine it with the quantization? And then...
Yeah, it's a great question. So in the movement pruning approach, we did go end to end and include quantization. And then also in this work, Edgebert, it kind of applies all combinations of things to try to test for sensitivity. So it does floating point quantization as part of the system. I don't have a kind of I don't have a simple answer for the impact, but it's certainly not. We haven't found that you need to do one or the other, that quantization breaks pruning or pruning breaks quantization. they seem to stack with each other. They're not orthogonal, but it seems like you can do both without kind of fully breaking your model.
Okay, so I was wondering, so for example, is there any like kind of the pattern, like or the rough guideline for do the quantization, like some kind of the like which part of your transformer is kind of the more sensitive to the quantization? Is there any
Interesting. Like
pattern exists there?
Which layer is, you mean?
Yeah.
Yeah. We do have a paper about this. I don't remember offhand exactly the details, but the paper from our group is called adaptive float, and it looks at the kind of quantization properties of transformer and notes that there are specific aspects to transformer structure, particularly its normalization, that make the range of values it uses quite different than, say, a CNN. And so you have to kind of be a little bit more careful about quantization aspects. But as far as I know, don't think that people in practice try to quantize different layers differently. But I'm not an expert on this, so I can't totally speak to it.
Okay. And also very interesting that, so in one of your slides, you mentioned about the future is kind of the efficient training, right? So, so from your perspective, so how do you think what is kind of the unique challenge or the opportunities towards the efficient training of the transformer for the NLP?
Efficient training. Yeah.
We know that, so the NLP transformer is kind of much larger than the vision transformer. The efficient training is even more challenging, especially for the group in the academia, right? We don't have enough resource like all those big companies they have.
Yeah, absolutely. So again, I'm not an expert on this topic, but Hugging Face is running this year. We're calling it's called Big Science. It's a year-long project to publicly train a GPT-3 size model. So we got a grant from the French government, and we're running this completely open source. And so we have a lot of engineers who are going through the specific details of actually running these large models efficiently in practice. And yeah, it's quite challenging. So there are really neat projects from NVIDIA and Microsoft called Deep Speed and Megatron LM that kind of go through the process for training these very large models across device. So in practice, what actually comes up are things like communication between GPUs, things like kind of training very large models within the memory storage of the device. So things like kind of checkpointing and kind of writing out intermediate activations to save memory. And then the actual operations underlying these systems are relatively standard to kind of just using kind of the most efficient implementations. And then there's been a lot of interest over the last couple of years in NLP in improving very long distance attention. So there are some approaches that attention, when you have very, very long sequences, can be the bottleneck during training. So how you avoid that or kind of approximate that aspect of it in practice. So lots in that space. I don't have any kind of concrete answer, but I can point you to a ton of resources.
Thank you. Thank you very much. So any questions from the audience? So if no more questions, so let's thank our speaker again. So Sasha, thank you so much for giving this wonderful talk. Okay.
Thanks, everyone.
Also thank everyone to attend our this week seminar talk. Let's meet next week. Thank you. Have a wonderful day, Sasha.
Bye.